Natural language processing is a field of computer science, artificial intelligence, and linguistics concerned with the interactions between computers and human languages. As such, NLP is related to the area of human-computer interaction. Many challenges in NLP involve natural language understanding, that is, enabling computers to derive meaning from human or natural language input, and others involve natural language generation. History. The history of NLP generally starts in the 1950s, although work can be found from earlier periods. In 1950, Alan Turing published an article titled Computing Machinery and Intelligence, which proposed what is now called the Turing Test as a criterion of intelligence. The Georgetown experiment in 1954 involved fully automatic translation of more than 60 Russian sentences into English. The authors claim that within 3 or 5 years, machine translation would be a solved problem. However, real progress was much slower, and after the ALPAC report in 1966, which found that 10-year-long research had failed to fulfill the expectations, funding for machine translation was dramatically reduced. Little further research in machine translation was conducted until the late 1980s, when the first statistical machine translation systems were developed. Some notably successful NLP systems developed in the 1960s were SHRDLU, a natural language system working in restricted blocks worlds with restricted vocabularies, and ELIZA, a simulation of a Rogerian psychotherapist, written by Joseph Weizenborn between 1964 to 1966. Using almost no information about human thought or emotion, ELIZA sometimes provided a startlingly human-like interaction. When the patient exceeded the very small knowledge base, ELIZA might provide a generic response, for example, responding to "my head hurts" with, "Why do you say your head hurts?" During the 1970s, many programmers began to write conceptual ontologies, which structured real-world information into computer-understandable data. Examples are Margie, Sam, PAM, Tailspin, Quam, Politics, and Plot Units. During this time, many chatterbots were written including Parry, Rector, and Jabberwocky. Up to the 1980s, most NLP systems were based on complex sets of handwritten rules. Starting in the late 1980s, however, there was a revolution in NLP with the introduction of machine learning algorithms for language processing. This was due both to the steady increase in computational power resulting from Moore's law and the gradual lessening of the dominance of Chomskyan theories of linguistics, whose theoretical underpinnings discouraged the sort of corpus linguistics that underlies the machine learning approach to language processing. Some of the earliest used machine learning algorithms, such as decision trees, produced systems of hard if-then rules similar to existing handwritten rules. Increasingly, however, research has focused on statistical models, which make soft, probabilistic decisions based on attaching real-valued weights to the features making up the input data. The cache language models upon which many speech recognition systems now rely are examples of such statistical models. Such models are generally more robust when given unfamiliar input, especially input that contains errors, and produce more reliable results when integrated into a larger system comprising multiple subtasks. Many of the notable early successes occurred in the field of machine translation, due especially to work at IBM Research, where successively more complicated statistical models were developed. These systems were able to take advantage of existing multilingual textual corpora that had been produced by the Parliament of Canada and the European Union as a result of laws calling for the translation of all governmental proceedings into all official languages of the corresponding systems of government. However, most other systems depended on corpora specifically developed for the tasks implemented by these systems, which was a major limitation in the success of these systems. As a result, a great deal of research has gone into methods of more effectively learning from limited amounts of data. Recent research has increasingly focused on unsupervised and semi-supervised learning algorithms. Such algorithms are able to learn from data that has not been hand-annotated with the desired answers, or using a combination of annotated and non-annotated data. Generally, this task is much more difficult than supervised learning, and typically produces less accurate results for a given amount of input data. However, there is an enormous amount of non-annotated data available, which can often make up for the inferior results. NLP using machine learning. Modern NLP algorithms are based on machine learning, especially statistical machine learning. The paradigm of machine learning is different from that of most prior attempts at language processing. Prior implementations of language processing tasks typically involved the direct hand coding of large sets of rules. The machine learning paradigm calls instead for using general learning algorithms often, although not always, grounded in statistical inference to automatically learn such rules through the analysis of large corpora of typical real-world examples. A corpus is a set of documents that have been hand-annotated with the correct values to be learned. Many different classes of machine learning algorithms have been applied to NLP tasks. These algorithms take as input a large set of features that are generated from the input data. Some of the earliest used algorithms, such as decision trees, produced systems of hard-if-then rules similar to the systems of handwritten rules that were then common. Increasingly, however, research has focused on statistical models, which make soft, probabilistic decisions based on attaching real-valued weights to each input feature. Such models have the advantage that they can express the relative certainty of many different possible answers rather than only one, producing more reliable results when such a model is included as a component of a larger system. Systems based on machine learning algorithms have many advantages over hand-produced rules. The learning procedures used during machine learning automatically focus on the most common cases, whereas when writing rules by hand it is often not obvious at all where the effort should be directed. Automatic learning procedures can make use of statistical inference algorithms to produce models that are robust to unfamiliar input and to erroneous input. Generally, handling such input gracefully with handwritten rules or more generally, creating systems of handwritten rules that make soft decisions is extremely difficult, error-prone and time-consuming. Systems based on automatically learning the rules can be made more accurate simply by supplying more input data. However, systems based on handwritten rules can only be made more accurate by increasing the complexity of the rules, which is a much more difficult task. In particular, there is a limit to the complexity of systems based on handcrafted rules, beyond which the systems become more and more unmanageable. However, creating more data to input to machine learning systems simply requires a corresponding increase in the number of man-hours worked, generally without significant increases in the complexity of the annotation process. The subfield of NLP devoted to learning approaches is known as natural language learning, and its conference Co-NLL and Peak Body SIGNLL are sponsored by ACL, recognizing also their links with computational linguistics and language acquisition. When the aims of computational language learning research is to understand more about human language acquisition, or psycholinguistics, NLL overlaps into the related field of computational psycholinguistics. Major tasks in NLP. The following is a list of some of the most commonly researched tasks in NLP. Note that some of these tasks have direct real-world applications, while others more commonly serve as sub-tasks that are used to aid in solving larger tasks. What distinguishes these tasks from other potential and actual NLP tasks is not only the volume of research devoted to them but the fact that for each one there is typically a well-defined problem setting, a standard metric for evaluating the task, standard corpora on which the task can be evaluated, and competitions devoted to the specific task. Automatic summarization, produce a readable summary of a chunk of text. Often used to provide summaries of text of a known type, such as articles in the financial section of a newspaper. Coreference resolution, given a sentence or larger chunk of text, determine which words refer to the same objects. Anaphora resolution is a specific example of this task, and is specifically concerned with matching up pronouns with the nouns or names that they refer to. The more general task of coreference resolution also includes identifying so-called bridging relationships involving referring expressions. For example, in a sentence such as "He entered John's house through the front door," The front door is a referring expression, and the bridging relationship to be identified is the fact that the door being referred to is the front door of John's house. Discourse analysis. This rubric includes a number of related tasks. One task is identifying the discourse structure of connected text, that is the nature of the discourse relationships between sentences. Another possible task is recognizing and classifying the speech acts in a chunk of text. Machine translation, automatically translate text from one human language to another. This is one of the most difficult problems, and is a member of a class of problems colloquially termed AI complete, that is requiring all of the different types of knowledge that humans possess in order to solve properly. Morphological segmentation, separate words into individual morphemes and identify the class of the morphemes. The difficulty of this task depends greatly on the complexity of the morphology of the language being considered. English has fairly simple morphology, especially inflectional morphology, and thus it is often possible to ignore this task entirely and simply model all possible forms of a word as separate words. In languages such as Turkish, however, such an approach is not possible, as each dictionary entry has thousands of possible word forms. Named entity recognition. Given a stream of text, determine which items in the text map to proper names, such as people or places, and what the type of each such name is. Note that, although capitalization can aid in recognizing named entities in languages such as English, this information cannot aid in determining the type of named entity, and in any case is often inaccurate or insufficient. For example, the first word of a sentence is also capitalized, and named entities often span several words, only some of which are capitalized. Furthermore, many other languages in non-Western scripts do not have any capitalization at all, and even languages with capitalization may not consistently use it to distinguish names. For example, German capitalizes all nouns, regardless of whether they refer to names, and French and Spanish do not capitalize names that serve as adjectives. Natural language generation. Convert information from computer databases into readable human language. Natural language understanding. Convert chunks of text into more formal representations such as first-order logic structures that are easier for computer programs to manipulate. Natural language understanding involves the identification of the intended semantic from the multiple possible semantics which can be derived from a natural language expression, which usually takes the form of organized notations of natural languages concepts. Introduction and creation of language multimodal and ontology are efficient, however empirical solutions. An explicit formalization of natural languages semantics without confusions with implicit assumptions such as closed-world assumption versus open-world assumption, or subjective yes-no versus objective true-false is expected for the construction of a basis of semantics formalization. Optical character recognition. Given an image representing printed text, determine the corresponding text. Part of speech tagging. Given a sentence, determine the part of speech for each word. Many words, especially common ones, can serve as multiple parts of speech. For example, book can be a noun or verb. Set can be a noun, verb or adjective. And out can be any of at least 5 different parts of speech. Some languages have more such ambiguity than others. Languages with little inflectional morphology, such as English, are particularly prone to such ambiguity. Chinese is prone to such ambiguity because it is a tonal language during verbalization. Such inflection is not readily conveyed via the entities employed within the orthography to convey intended meaning. Parsing. Determine the parse tree of a given sentence. The grammar for natural languages is ambiguous and typical sentences have multiple possible analyses. In fact, perhaps surprisingly, for a typical sentence there may be thousands of potential parses. Question answering. Given a human language question, determine its answer. Typical questions have a specific right answer, but sometimes open-ended questions are also considered. Relationship extraction. Given a chunk of text, identify the relationships among named entities. Sentence breaking. Given a chunk of text, find the sentence boundaries. Sentence boundaries are often marked by periods or other punctuation marks. but these same characters can serve other purposes. Sentiment analysis extracts subjective information usually from a set of documents, often using online reviews to determine polarity about specific objects. It is especially useful for identifying trends of public opinion in the social media, for the purpose of marketing. Speech recognition, given a sound clip of a person or people speaking, determine the textual representation of the speech. This is the opposite of text-to-speech and is one of the extremely difficult problems colloquially termed AI complete. In natural speech there are hardly any pauses between successive words, and thus speech segmentation is a necessary subtask of speech recognition. Note also that in most spoken languages, the sounds representing successive letters blend into each other in a process termed co-articulation, so the conversion of the analog signal to discrete characters can be a very difficult process. Speech segmentation, given a sound clip of a person or people speaking, separate it into words. A subtask of speech recognition and typically grouped with it. Topic segmentation and recognition, given a chunk of text, separate it into segments each of which is devoted to a topic, and identify the topic of the segment. Word segmentation, separate a chunk of continuous text into separate words. For a language like English, this is fairly trivial, since words are usually separated by spaces. However, some written languages like Chinese, Japanese and Thai do not mark word boundaries in such a fashion, and in those languages text segmentation is a significant task requiring knowledge of the vocabulary and morphology of words in the language. Word sense disambiguation, many words have more than one meaning. We have to select the meaning which makes the most sense in context. For this problem, we are typically given a list of words and associated word senses, for example from a dictionary or from an online resource such as WordNet. In some cases, sets of related tasks are grouped into subfields of NLP that are often considered separately from NLP as a whole. Examples include information retrieval. This is concerned with storing, searching and retrieving information. It is a separate field within computer science, but IR relies on some NLP methods. Some current research and applications seek to bridge the gap between IR and NLP. Information extraction. This is concerned in general with the extraction of semantic information from text. This covers tasks such as named entity recognition, coreference resolution, relationship extraction, etc. Speech processing. This covers speech recognition, text-to-speech and related tasks. Other tasks include stemming, text simplification, text-to-speech, text proofing, natural language search, query expansion, automated essay scoring, true casing, statistical NLP. Statistical natural language processing uses stochastic, probabilistic and statistical methods to resolve some of the difficulties discussed above, especially those which arise because longer sentences are highly ambiguous when processed with realistic grammars, yielding thousands or millions of possible analyses. Methods for disambiguation often involve the use of corpora and Markov models. Statistical NLP comprises all quantitative approaches to automated language processing, including probabilistic modeling, information theory, and linear algebra. The technology for statistical NLP comes mainly from machine learning and data mining, both of which are fields of artificial intelligence that involve learning from data. Evaluation of natural language processing, objectives. The goal of NLP evaluation is to measure one or more qualities of an algorithm or a system, in order to determine whether the system answers the goals of its designers, or meets the needs of its users. Research in NLP evaluation has received considerable attention, because the definition of proper evaluation criteria is one way to specify precisely an NLP problem, going thus beyond the vagueness of tasks defined only as language understanding or language generation. A precise set of evaluation criteria, which includes mainly evaluation data and evaluation metrics, enables several teams to compare their solutions to a given NLP problem. Short history of evaluation in NLP. The first evaluation campaign on written text seems to be a campaign dedicated to message understanding in 1987. Then, The Parsing GEIG project compared phrase structure grammars. A series of campaigns within Tipster project were realized on tasks like summarization, translation and searching. In 1994, in Germany, the Morpholympics compared German taggers. Then, the Sense-Wahl and Romance-Wahl campaigns were conducted with the objectives of semantic disambiguation. In 1996, the Sparkle campaign compared syntactic parsers in 4 different languages. In France, the Grace project compared a set of 21 taggers for French in 1997. In 2004, during the Techno-Languese project, 13 parsers for French were compared. Large-scale evaluation of dependency parsers were performed in the context of the Co-NLL shared tasks in 2006 and 2007. In Italy, the Evalita campaign was conducted in 2007 and 2009 to compare various NLP and speech tools for Italian. The 2011 campaign is in full progress, Evalita website. In France, within the ANA Passage project, 10 parsers for French were compared, Passage website. Different types of evaluation, depending on the evaluation procedures, a number of distinctions are traditionally made in NLP evaluation. Intrinsic versus extrinsic evaluation. Intrinsic evaluation considers an isolated NLP system and characterizes its performance mainly with respect to a gold standard result, predefined by the evaluators. Extrinsic evaluation, also called evaluation in use, considers the NLP system in a more complex setting, either as an embedded system or serving a precise function for a human user. The extrinsic performance of the system is then characterized in terms of its utility with respect to the overall task of the complex system or the human user. For example, consider a syntactic parser that is based on the output of some new part of speech tagger. An intrinsic evaluation would run the POS tagger on some labeled data, and compare the system output of the POS tagger to the gold standard output. An extrinsic evaluation would run the parser with some other POS tagger, and then with a new POS tagger, and compare the parsing accuracy. Black box versus glass box evaluation. Black box evaluation requires one to run an NLP system on a given dataset and to measure a number of parameters related to the quality of the process and, most importantly, to the quality of the result. Glass box evaluation looks at the design of the system, the algorithms that are implemented, the linguistic resources it uses, etc. Given the complexity of NLP problems, it is often difficult to predict performance only on the basis of glass box evaluation, but this type of evaluation is more informative with respect to error analysis or future developments of a system. Automatic versus manual evaluation. In many cases, automatic procedures can be defined to evaluate an NLP system by comparing its output with the gold standard one. Although the cost of producing the gold standard can be quite high, automatic evaluation can be repeated as often as needed without much additional costs. However, for many NLP problems, the definition of a gold standard is a complex task, and can prove impossible when inter-annotator agreement is insufficient. Manual evaluation is performed by human judges, which are instructed to estimate the quality of a system, or most often of a sample of its output, based on a number of criteria. Although, thanks to their linguistic competence, human judges can be considered as the reference for a number of language processing tasks, there is also considerable variation across their ratings. This is why automatic evaluation is sometimes referred to as objective evaluation, while the humankind appears to be more subjective. Standardization in NLP. An ISO subcommittee is working in order to ease interoperability between lexical resources and NLP programs. The subcommittee is part of ISO TC 37 and is called ISO SC4. Some ISO standards are already published, but most of them are under construction, mainly on lexicon representation, annotation and data category registry. The future of NLP. NLP research is gradually shifting from lexical semantics to compositional semantics and, further on, narrative understanding. Human-level natural language processing, however, is an AI-complete problem. That is, It is equivalent to solving the central artificial intelligence problem, making computers as intelligent as people, or strong AI. NLP's future is therefore tied closely to the development of AI in general. See also, List of natural language processing toolkits, biomedical text mining, compound term processing, computer-assisted reviewing, controlled natural language, deep linguistic processing, foreign language reading aid, foreign language writing aid, language technology, latent semantic indexing, LRE map, natural language programming, reification, spoken dialogue system, intelligent systems, transderivational search, references. Further reading.